So this is AP Chemistry for Hoover High School, and this is your Day 64, Lesson 37 on equilibrium rice tables. So I've given you about 10 of these problems, but as you get good at them, they'll go faster and faster. So let's go ahead, get started. These are just references to where I got the problem. You don't need to concern yourself with that. So the first problem gives you this reaction. Of course, that should be lowercase to subscript O2 oxygen, and to SO3 lowercase there as well. Okay, so you'll see some of those throughout that I did not change. Okay, so question, or the statement is, if the initial concentration of SO2 and O2 are 0.1 molar and the equilibrium concentration of O2 is 0.75 molar, what is the value of Kc? So almost all of these problems, they're giving you a value of Kc and asking you to find the equilibrium what the equilibrium concentrations will be. Remember what that is. That's when the reaction, it runs its course. It's either gone from left to right or right to left or whatever it's going to do, and it finally finds its happy place right somewhere around the middle, or could be middle, could be one side, could be the other, and that's where it's going to settle. So you're either asked to find that. In order to do that, you have to be given a equilibrium constant, or you're given the concentrations and you're asked to figure out the equilibrium constant for that reaction. An equilibrium constant for this reaction at a given temperature is always going to be constant. That doesn't change. As long as the temperature doesn't change, the equilibrium reaction for this SO2-O2 to SO3 reaction will always be the same. That's why it's called a constant. Okay, so let's start filling in the table. First thing you want to do is you want to write the reaction, and I like to write the reaction exactly as it appears. So, you can put the plus sign there if you want. And over here you have O2, 1 mole of O2. I kind of like to write those 1 coefficients to remind me that that's what we're dealing with. It's not required. And then here's the arrow. You'll never see this in a book where they write the arrow there, but I like to. So I like to remember which side is reactants and which side is products. So there you go. Okay, so that's what the reaction should look like up there. Okay, start filling in the blanks. Initial concentration, these two, that's key. Be sure you know which type, and that's these two. So we're going to go ahead and put these up here. All right, and it says equilibrium concentration of O2. So that's going to be this down here. It's O2, and it's on the equilibrium line. So that's going to be this. Okay. And then one other thing that you can fill out right now is if they don't tell you any initial concentration of either a reactant or a product, you can assume it's 0. That's always true. That's never a trick question where that's not going to be true. That'll always be true, okay? All right, now the change line is always the one with the variables in it, the ones with the x's in it. So we are going in this case since we have reactants over on this side and no products, we're going totally from left to right in this reaction. So that means these are going to be subtractions over here. So it's minus x. And then in front of x, you always put whatever the coefficient in front of that particular reactant is. Okay, this one's same thing. It's minus x. And just to be consistent, at least at the beginning, I'll write the ones there like that. Okay, and this one is going to go, it's going to be x, it's going to be 2x. In other words, we don't know. It's positive because it's increasing. It's on the product side. We don't know how many moles of this is happening. We don't know. All we know is it's the same number of moles of SO3 as moles of SO2 are being consumed because it's 2 to 2. So it's 2 to 2. 1. Again, you just remember, you put whatever the coefficient is there, coefficient there, coefficient there. Okay? So now we can add these two and get 2x down here. We can subtract these. And get that. So we filled out the table. So now what can we figure out? Well, we can go right ahead and figure out x without having to set up a law of mass action, which we often have to do. We'll eventually have to do that to get Kc because it's asking us what's the Kc. But right here, you have a complete algebraic equation. You have a number, minus 1x gives you a number. So this is just an algebra problem right here. So you can go ahead and directly solve for x. Okay, so I'll just do that right here. Okay, so I'm going to take this complete algebraic equation, set it up here. So 0.1 minus 1x equals 0.0750. Okay, so what I want to do is I'm going to subtract 0.075 from both sides. Okay, that's what we get. And we're going to move the x over, so add x to both sides, and you end up with x equals 0.25. Okay, so I hope that wasn't an algebra trick for you there. All right, so we know what x is. So in order to get Kc, we have to have the equilibrium concentrations of everything to plug into the law of mass action. Okay, so let's go ahead and do that first, and then we'll write the law of mass action. You can do that in either order, but let's go ahead and get the concentrations. So we're going to take this number x and plug it back in here for x, and back in here for x, and we'll get the equilibrium concentrations of those. So I'm going to do that over here. So the concentration of SO2, you don't have to write of 2SO2, it's just of SO2. That's going to be the concentration of SO2. You've already taken the 2 into account here. Okay, and that's going to equal 0.1 minus 2.025, and that's going to give us 0.05. This one we already have. And for the SO3, x, there's x. And that also gives us this 0.05. Okay, so with the concentrations and the law of mass action, we can figure out what K is. So let's always write the general law of mass action before you plug in numbers, okay? Kc equals, include the 2 in the coefficient, it goes up in the exponent, like that. So again, it's concentration of SO3 raised to the second power, raised to the power of whatever its coefficient is. On the bottom we have the reactants, this. So it's 2SO2, so that's going to be SO2 raised to the second power, and the concentration of O2 raised to the first power. Okay, there you go. Now, you already know these numbers, these concentrations, they're right there. So we're going to plug those in. SO3 is 0.505. Okay, I'll use parentheses now since it's a math equation, and that's raised to the second power. SO2 is right there. It's also 0.05 squared. Okay, and O2 right there is this, to the first power. Okay, and now it's just math, so I'll come over here and write my answer. Okay, here we go. We are going to go on to number 2 now. So let's start right here. Initial concentration of NH3, ammonia, is 1. Reacts according to this equation. At equilibrium, it gives you the pressure of NH3. So you get the pressure of NH3 twice. Initial and equilibrium. So let's fill that in. First of all, write the reaction. Again, my preference is to write it with all the plus signs and arrows, and that's not a plus sign there, that's an arrow there. That way you remind yourself, the plus signs aren't important, but the arrows remind you which side is products and which side is reactants. Okay, and then you got N2 and 3H2. So there's the complete reaction. That would be the plus sign right there. Okay, so we're going to go ahead and we're given two concentrations of this. This one is initial, 1.0. And this one is final. So that's a pretty simple little problem. You can maybe do that in your head, but let's set it up properly. So there's going to be some unknown there that we have to figure out. But here's the trick. Remember, this is minus 2x. Whatever that number is, we're not really interested in this difference. We're interested in what this x value is, okay? So we could come down here. Okay, I'm going to add 2x to both sides, and I'm going to subtract 0.8 from both sides in the same step. Okay, I hope that's not too tricky. So you end up with 0.2 on this side, and you end up with 2x over on the right side. So if that's tricky for you, talk to me and we'll practice that. Okay, I just did two algebra steps in one. Added 2x to both sides, so you end up with 2x over here. Subtracted 0.8 from both sides, so this goes away, and you end up with 1 minus 0.8 is 0.2. Okay, now finish off by dividing by 2. So now we know what x is. X equals 0.1. Okay, so now let's finish writing this in terms of variables. If we're not given concentrations initially for anything, we assume it's 0. And this is going to be a product, so it's going to be increasing. We started off with 1 molar over here and 0 here. So there's nowhere for this to go but up. It's got to increase. And it's going to be x, that's the unknown amount, and it's going to be 1x. And it's a plus because it's increasing. So 0 plus 1x is 1x. And over here, same thing, 0 plus some number x, but you're going to multiply it by the coefficient there. Whatever it is, in other words, whatever this amount is, it's going to be 3 times this amount, because this formula tells you this is 3 times that. So that's going to be 3x down there. Okay, so we know what x is. So 1x, so this is, I'll just write it down below here. This is 0.8. This is 1 times 0.1, that's x. 1 times x, that's going to be 0.1. And this is 3 times x, which is 0.1. That's going to be 0.3. Okay, so you have that, you have that, you have that as your equilibrium concentrations. And you're trying to find out what the equilibrium constant, Kp, is. So write it in general terms first, because I want to be sure you know how to write these laws of mass action. Okay, it's an easy mistake to make, what I'm about to show you. So it's Kp, and it's products on the top. So that is N2, concentration of N2 to the first power. You can write it if you want, times concentration of H2 to the raised to the coefficient third power. A common mistake is to write that as 3H2. It's not 3H2. The 3 becomes the exponent. It doesn't go inside of those brackets there, okay? It's just the concentration of H2. And then that's going to be over the reactant, which is this. And you raise that to the second power. Okay, so now we can just plug in the numbers. N2 right there. I'll use parentheses since we're doing math now. Doesn't matter. Absolutely does not matter. H2 is right there. And we've got to raise that to the third power. NH3 is right there. We've got to raise that to the second power. So you do the math on this. On a serious test, I would recommend you play it safe. Don't try to knock that down in one calculation. I can do it. Probably a lot of you can do it. I would play it safe. I would write this out and do the calculations one at a time. 0.1. So I'm bringing everything down here. Let me get rid of that because it's confusing. Okay, 0.3. So 0.3. Show you how to do that. 0.3 to the third power. Little caret there, hat. And then raised to the third power. And that gives you 0.027. So I'm going to do that calculation and then write it down. And then that's going to be over 0.8. And I don't need to use the caret because there's an x squared function on the calculator. So it's x squared. And that's going to be 0.64. Now you can do this in one calculation. This times this divided by that. That's something you can do in one calculation. And that gives us Kp equals, I'll go up here and write it up here. The final answer is the equilibrium constant for that pressure is 0.0042. No units of measure. Okay, so now that you know that, at some temperature, we should be stating that it's at a constant temperature, or to give the temperature like they do in many of the problems that I've shown you before. Once you know that number, you can, if you knew the concentration of one of these, or you somehow could come up with an algebraic equation like that, you can use that number to figure out what X is, and then figure out what the equilibrium concentrations of every product and reactant are. Okay? That's the way you do that. Okay. Believe it or not, eventually, if you'll practice these, probably as many as we do on this, you'll get to where you can look at these without even filling out the rice table and figure out, basically figure out how to set up your equation. So here we find Kc, so that's what we're looking for, Kc. You have 0.1 molar of H2 and I2 are present initially, and 0.134 molar of Hi is present at equilibrium. So these two are top row up here, or second row actually, and the other one, the last one, is bottom row. So let's write the reaction. Okay, and let's go ahead and put these in 0. And there's a coefficient of 1 here. So that's going to be minus 1x. Same thing here. Same initial concentration. It's one coefficient of 1. So this is going to be this. And I'll just put minus x here. Okay, you assume that you didn't start with anything here, but they did give you the equilibrium. So that goes there. Okay, and it's 2. It's going to be adding because this is a product. So you can't go in below 0, right? So you got to go up. No place to go but up. So it's going to be x, and since the coefficient there is 2, it's going to be 2x. So what can we figure out here? Well, 0 plus 2x equals 1.34. Let's just set up a simple algebraic equation. 0 plus 2x equals... Okay, we can just obviously ignore that 0. So it's 2x equals 0.134. So we're going to divide both sides by 2. And that means x equals 0.67. Okay, so here we have, this one's going to be 0.1 minus, I goofed. Got to be careful on these. Why it might be useful to use a calculator. It should be 0.067. Okay. All right, so that's going to be X. So let's just come over here and write our concentrations down. The concentration of H2 equals 0.100 minus okay, so there's the concentration of that. That's really what goes there, is that number right there. Okay, and just do the other two. Calculation needed, that was given to us. Okay, so write the law of mass action and then plug those numbers into it. I'm trying to find Kc, so Kc. Okay, there's our product that goes on top. And it's squared. To the first power. To the first power. Okay, now plug in the numbers. Okay, and calculate that again. You want to really play it safe, do that first, write it down, then divide by this, if you feel like you need to do. What I'm going to do 0.134 x squared equals, divided by 0.033 equals, divided by 0.033 again equals, and there you get 16.5 is your Kc value. I'll put 16 there. Whatever. Not worried about sig figs right here. So that's the Kc value for this at some certain temperature. Okay. And I would state assumptions like that on the AP exam. If they didn't say that, I would say the temperature must remain constant. State your assumptions. Is it wrong if you don't? I don't know. It depends if they might expect that or not. So just be as thorough as possible. Okay, 4. Okay, decomposition of this. And again, this should have been lowercase. So let me write it properly. And there should have been a double arrow there in SO2, so that wasn't good. One thing you want to be sure when you write that out is be sure it's balanced. And yeah, it's balanced. That and that's that. Okay, so that's all good. Okay, so decomposition, and it has concentrations of this, this, and this, and a Kc. So compute Q. Okay, that's the way this was worded when I copied this problem from I get this from the University of Kentucky site, and so you assume those are equilibrium constant. Oh no, I take that back. It's a Q problem. So you don't know what the equilibrium concentrations are. You just know what K should be at equilibrium. So when you calculate Q, you're going to simply compute it exactly the same way as we did earlier to figure out K, and then you're going to see if your Q is greater than K. If it is, that means remember what K is in general. K is products over reactants in some fashion, in some equation. So if I put these in and I get a Q value with these concentrations that's greater than K, that means my products are too big for my reactants. I have too much product for the amount of reactant to be at equilibrium. If I get a Q that's less than K, then to make this less than my K value, my reactants would have to be too much. I'd have to have too much reactant for the amount of product. So what does that mean? If the Q is too big, is bigger than K, the reaction is going to move to the left. It's going to move back away from making products. It's going to disassemble some of the products or decompose them and produce reactants. If, on the other hand, the Q is less than K, it means it has too much reactants. It wants to get in balance by getting fewer reactants and producing more products so that it gets back into the balance of that K. Okay, so just remember, Q greater than K moves to the left. Q less than K moves to the right. So let's figure out what it is. So Q is going to equal, be sure we have our reaction correct here. So it's these two on top. Those are the products, and this is the reactant. So these two are the products. There's no coefficients there. It's ones, ones, and ones. So it's simply going to be 0.100. That's for this. I should be writing this out first, like a law of mass action. Okay, now I can come over here and plug in the numbers. These two are both 0.1. And the one on the bottom is also 0.1. Okay. Everybody's at 0.1. Okay, so clearly 0.1 and 0.1 are going to cancel, so you're left with just 0.1, that. All right, so Q is 0.1. So let's come over here and write that down here. Q, for those concentrations, equals 0.100. So you can see that this number is greater than that number. Okay, because that has a 0 in the first position after the decimal, that has a 1. Q is greater than K, so write that out. Q is greater than K, C. So this is going to favor, it means there's too much product for the amount of reactant. That's why this number turned out to be bigger than this number. So that means that it's going to favor reactants, meaning it's going to move backwards towards reactants. So learn that terminology, that expression. Okay, and I don't have a lot of room to write here. I'll just write the word backwards down here. It's going to move back from products back to reactants. Okay, and that's your answer. Okay, that's what the question wants to know. Okay, here we go. Let's do another one. I don't want this video to go much past 30 minutes, so I'm not sure where I am. I'm right about a little bit under that right now. Okay, so here's a reaction again. I left off the arrow. So that's why it's good to watch these videos. I can correct those things. So a reaction from 2A to B. So that would be a composition reaction. It's two of something combining to form something different. Okay, and it gives you a concentration for A and B. And will the reaction proceed forward or reverse direction? It's telling you what the Kc is. So you're going to calculate the Q. And you're going to figure out, is the Q bigger than the K or less than the K, okay? Again, just like the previous problem, you don't need a Rice table. So let me write the reaction down here a little better here. 2A, reversible reaction going to B. Okay? So again, when you're doing these and you're watching the video like this, go ahead now. You've seen an example up above. See if you can do this problem on your own. Okay. Once you saw that correction, you might have done this ahead of me, this video, and you said, I didn't know what that's talking about. That's because I left the arrow out. So that's why it's good to watch the videos. Okay, so go ahead and see if you can do. Just pause the video. Come back when you're done. See if you get the right answer. You do have the answer down here. You always have the answers on these problems. Okay, so I'm going to go ahead and do this. So the law of mass action for this, well, actually the Q equation is going to be the concentration of B over the concentration of A, and it's going to be squared because it has a coefficient of 2. Concentration, so B is 0.350. On the top and on the bottom is A, which is 0.250, and you got to square that. So go ahead and run those numbers. And it's 0.350 divided by 0.250 squared. And PEMDAS says it's going to do that square on the bottom before it does the division. and we get 5.6 equals Q. Okay, that's really not answering the question. Kc is 0.5. Okay, so 5.6, which is Q, is greater than 0.5. In other words, Q is greater than Kc. That means, again, write this out. You got Q, just like Kc, is products over reactants. So you have too much on top for the amount on bottom. That's why this number is too big. Too much up here, not enough down here. So that means this is going to want to move backwards. It's going to want to move from products back to reactants. So again, it's going to favor reactants. It's going to move towards reactants. That's backwards. Okay, and that's your answer, and you know that's your answer. That's your answer. Okay, that's how you do that. All right. See if I can sneak in one. Okay, so let's wrap up with number 6. So we've seen this equation before, decomposition of ammonia. So if equilibrium concentration of N2 and H2 are 0.5 and 0.1 molar respectively, what is the equilibrium concentration of NH3? All right, so let's go ahead and draw a quick little rice table here. Try to do it neatly. I'm not going to measure everything, but try to do it kind of neatly. Okay, close enough. All right, so here we go. And we have a total of 3 products reactants together, so we're going to need 3 spots for those. Okay, good enough. So here's rice, reaction, initial, change, equilibrium. Okay, we're going to write the reaction just like you see it there. Okay, there's the arrow right there. Again, my preference, I just write it exactly like a reaction, just like that. The arrow is the important thing, so I don't forget which side is products and which side is reactants. A lot of the ones you see in the book don't do that, and it's easy to, you can get confused. You can forget which side's which. Okay, so here we go. So what can we fill in? We have 9 boxes down here to fill in. What can we fill in? All right, so equilibrium concentrations of N2. So there's N2 is 0.5. So here's N2, here's equilibrium. It's 0.5, not initial, it's equilibrium. I'm going to omit these zeros at the end, okay? They're just taking up space. Okay, and H2 is 0.1. I'm not worried about significant figures here. So this is 0.1 down here. All right. Now, we don't even know where this is starting. We know nothing about where this started. We don't know whether this started at 0. This could have started with all products and moved backward to reactants. It could have started with all reactants and moved forward to products. We don't know. They didn't give us anything. I mean, if they had given us that there was some concentration of this, what I've told you, you can then assume that there's nothing over here. Or if they'd given us concentrations, initial concentration of this, you could assume, and they didn't tell you anything about this, you could assume there was nothing. They didn't give us anything. Okay, the good news is you don't need it, all right? You have 2 equilibriums. If you have 2 equilibrium concentrations and a KEQ, it should really be KC. Problem set that I copied this from said equilibrium, but it's a concentrate. They're molar, so it's concentrations. So you have these 3 numbers. That's good enough. Go ahead and write the law of mass action. Okay, so it's products on top. Raised to the first power, so this is raised to the first. You don't have to write it. Okay, raised to the third power. And then reactant on the bottom, and that's what you're trying to find. That's raised to the second power. Okay, so there it is. So we know this, and we know this. So we know 3 of the 4 variables here, unknown variables here, so we can figure out this. All right, so go ahead and fill in the numbers. This is 3.81. N2 is 0.5 at equilibrium. Remember, before you plug it in, it's got to be an equilibrium value, not an initial value. Be sure that's where you are. And we are. Okay, and this is 0.1. And that's raised to the third. Down here, you've got NH3 squared, and we're trying to find NH3. Okay. All right, what I'm going to do to both sides is multiply both sides by NH3 squared. It's just an algebra problem at this point. Okay, so these cancel. And now I'm going to, in the same step, I'm going to go ahead and divide by 3.81. And what we're trying to do is get this by itself, isolated on one side of the equal sign. This cancels. So it's 0.5 times 0.1 times... Is that right? That's cubed, right? Yeah. It's 0.5 times 0.1 cubed divided by 3.81. I always like to do powers first, but the calculator knows PEMDAS. It will do the power first, but I like to do it first just to be sure I get it done. So 0.1 caret 3, that's 0.1 cubed, gives us this, 0.001. Now you're going to multiply that by 0.5, rather. Equals. I like to hit equals each time. Let's just get that. So now we have this, all of this. Now we're going to divide by 3.81. What it's telling me is the answer to the last part when I hit equal divided by 3.81. In case you have a different calculator. Okay. And it's 0.000131234. There's a problem with the memory on this specific calculator, so I'm going to write that down. So that means that NH3 squared equals that. That's a lot of significant figures. 0.00013. I'm going to go with that. Okay, so that's what I have from the calculator. Now I need to take the square root of that. Okay, second. And then x squared gives me a square root. 0.00013. Close the parenthesis, hit equal, and I get 0.0114. So the concentration of NH3 equals 0.0114, and don't forget unit of measure, that's molar. Okay, and that's your answer right there. I ended up with 1.5 there. I'm not sure why. Anyway, it's close. All right, so that's how you do that. I'm going to wrap this particular video, do the rest of the problems on another video so you can get started on this one. Okay, so I'll see you on the part 2 video of this.